Hi, I'm Teng Dahan from VGG Oxford. This is a presentation for our BMVC paper, Turbo Training with Token Dropout. Learning from videos is very attractive. First, the amount of training data is never a problem. For example, there are about 82 years of videos uploaded to YouTube every day. Videos contain much more information than static images, like long-term activities or stories. Also, videos contain multiple modalities like audio and text. However, learning from videos is becoming very challenging recently. Let's check a few recent great papers in video topics. 64 TPUs, 64 GPUs, batch size of 1000, another 64, 128 A100 GPUs. All of these papers are great, but the resource requirement for video research is becoming very high, which stops many researchers to make contribution in this area. Also, this large-scale training brings negative impact to the natural environment. In this paper, we want to speed up the video training. Since the visual information from video is highly redundant, like the high FPS or the static video frames, we work on the question, can we train video model with a sparsely sampled input data, but still perform well on downstream tasks? Reducing input data brings two benefits. It improves the training efficiency, also reduces the memory requirement. Our method benefits from the design of vision transformers, or VITs. For vision transformers, the input images or videos are cut into visual patches or visual tokens. Then all of these visual tokens are encoded by a transformer which consists of self-attention operations and gives a visual feature. Since videos are highly redundant, we speed up the vision transformers by dropping a large portion of visual tokens, which quadratically reduces the complexity of vision transformers. The token dropout operation is inspired by masked autoencoder, or MAE, where they train a VIT-based autoencoder on the masked visual input to reconstruct the masked pixels. Their objective is to learn a strong visual representation, whereas we want to use this token dropout operation to speed up the video training in multiple scenarios. Our method is shown here. We randomly drop the visual tokens to save computation. We also use MAE loss as the auxiliary loss to regularize the model, training together with other tasks of interest. Additionally, we propose partial MAE to further reduce the computation of the MAE loss, that our model only reconstructs a portion of visual patches rather than all of them. Let's see how it works. Here we show the turbo training is extremely memory efficient. It enables to load 8 times more input frames with the same amount of GPU memory. Or, with the same number of input frames, it saves up to 8 times GPU memory. On video tasks, we first show that turbo training enables fast fine-tuning for action classification tasks on UCF 101. Fine-tuning pre-trained models is a common scenario of video training. Turbo training achieves 4 times of speed up, while still maintaining the competitive performance. Vision language pre-training is an attractive research area that gives a strong visual representation but requires a huge amount of computation. We experiment visual language pre-training on HTM-AA, the automatically aligned version of How-To 100 million dataset. We take it for visual textual contrastive learning. We show that turbo training brings significant speed up for vision language pre-training. When training for a same amount of time with the same hardware resource, it gives a huge performance gain compared to classic VIT training without token dropout, mainly due to the larger batch size and faster iterations. Without turbo training, the vision language pre-training is almost impossible to achieve with limited computation resource. We evaluate the model performance on visual textual alignment task on HTM-aligned dataset. The visual features learned by turbo training method achieves state-of-the-art performance on this task. Turbo training enables end-to-end training of long video tasks because it enables loading much more video frames. We experimented the long video activity classification task on breakfast and coin dataset. For this task, the model requires to watch the minutes-long video to classify the activity. Previous works adopt two-stage training on this task, that first extracting visual features for each frames or short video clips, then training a temporal model on the frozen features. Turbo training achieves single-stage end-to-end training by loading up to 64 frames and gets state-of-the-art or competitive performance. Thank you.